Okay, let's get this show on the road. Hello, everyone. Hope you're well. Welcome to another edition of Math 1203. Let's actually jump into it because we were in the middle of stuff last time. Yeah, there we go. Make sure I can see you guys. Make sure I can see the chat. Okay, all right. So last time we started a new topic. Was the topic of indeterminate forms and L'Hopital's rule. L'Hopital's rule. So this was a new limit technique that we could use derivatives to help us take limits in very specific situations. So we had these things called indeterminate forms. These were limit forms which looked like they were strange forms in the sense that we couldn't interpret them or evaluate them at face value because they had very different ideas associated with them. Things like infinity to the zero, 1 to the infinity, infinity minus infinity, 0 times infinity, 0 to the 0, infinity over infinity, 0 over 0. All these guys are kind of weird because in one sense you would think they're one thing, but in another sense you think they're something else. And you could never really be sure at face value. You had to do something else to be sure. And they're not obvious. L'Hopital's rule was something that helps us deal with two of these types of indeterminate forms. So there are 7 types I expect you to know about, and 2 of them we can use L'Hopital's rule. It's very important that you remember that you can only use L'Hopital's rule in these 2 cases. You cannot use it in the other cases. If you're in the other case, a lot of times you can rewrite them to be able to use L'Hopital's rule, and we're going to be doing that. Sometimes after rewriting them, you might realize you don't even need L'Hopital's rule. So we'll see that coming up. L'Hopital's rule itself basically says that if you have a limit of a division and you want to find that limit, but you notice that the limit goes to 0 over 0 or infinity over infinity, then you can apply this rule here, which says that the original limit is going to be the limit of the derivative of the numerator divided by the derivative of the denominator. That's it. Whenever the original limit exists, this new limit of derivatives will actually give you the same answer, strangely enough. There are some requirements there about the continuity of the G, but I don't think you have to worry about that. Like if you see a situation where you think L'Hopital's rule can work, you check the conditions, which I'll be showing you, it can work. Okay, so the functions we're using in this class are going to be nice. You should also note that you can use L'Hopital's rule repeatedly. We might see that soon as well. And we had some examples that we were going through, but we only went through 2 of them. So we have the limit of e to the x over x. Notice that this went to infinity over infinity. That's how we're going to check. We're going to check what does it approach. As x approaches infinity, e to the x approaches infinity. And as x approaches infinity, x approaches infinity, the denominator. So this goes to infinity over infinity, which gives us L'Hopital's rule, which allows us to differentiate the top, differentiate the bottom. And that new limit, which is more obvious, is going to give us the same answer. We saw a similar thing with ln x over x. Went to infinity over infinity. And by applying L'Hopital's rule, we could see that it goes to 0 ultimately. Now, just so you know, we could have solved these guys without L'Hopital's rule. Right? So, yeah, which I mentioned here. And I mentioned here. Right? So with limits like these, I probably wouldn't use L'Hopital's rule because it's just not necessary. You could just say, oh, this is bottom heavy, it goes to 0, and I'd be fine with that. But I just wanted to illustrate with something that you guys kind of know where it was going to kind of, convince you that this is a thing that's going to work out, even though, the proper way to convince someone is with a mathematical proof, but that doesn't work in this class, I don't think. So now what we're going to do is we're going to do the rest of these examples and move on to another topic. So let's do that. going to do this guy. X ln x. C limit as x approaches 0 of x ln x. Okay. Now, what you're going to do is you're going to sort of look at what this guy is going to look like. You'll notice that it will approach, as x approaches 0 from the right, goes to 0, right? Times as ln of x, if you approach x approaches 0 from the right, ln of x, you know the graph goes down like that. It's going to go to negative infinity. This is a 0 times infinity indeterminate form. Indeterminate. But not conveniently so, right? So it's indeterminate, but it's not something that is usable to us at this moment in its present form. So we had to get this into a nicer form. Any suggestions for that? To use algebra to get this into a nicer form. Well, one trick is to do this really strange thing that very usually you won't do. But if you want to create a division from multiplication, it's an option. I can take the reciprocal of a reciprocal to get the thing in the, to get the reciprocal of, okay, basically what I'm saying is if you have 1 over x, it's the same as x, right? So that's what I'm going to do. Instead of writing the x, I'm going to write 1 over x. That's the same thing, right? Keep, change, flip, all that good stuff. So I could rewrite this like that. I can write 1 over x because I know my x is not 0. It's only getting close to 0 as the limit would require. And now you'll notice that if I were to check the limit, as x approaches 0 from the right, the numerator goes to infinity. As x goes to 0 from the right, the denominator goes to positive infinity because we know the graph of 1 over x on the right side. So this is infinity over infinity. So at this point, you notice, L'Hopital's rule applies. So now you take it to the hospital. That original limit is going to be equal to the same limit if I took the derivative of the top and divided by the derivative of the bottom. That limit is going to give me the same thing. So now you would notice that if I were to check what this would approach to see, maybe it approaches something obvious. If I look at the top 1 over x as x approaches 0 from the right, that goes to infinity. If I look at the bottom, minus 1 over x squared as x approaches 0 from the right, goes to negative infinity. So at this point, you go L'Hopital's again, because I said you could repeatedly do it. But if you did that, that would be not great. It would not be wrong, but it would not be great because you would sort of end up in the same situation, and you can check to see this. The top is going to go to 1 over x squared minus 1 over x squared. The denominator is going to go to 2 over x cubed. You'll end up in the same situation. And what do? L'Hopital's again. You realize that you end up in the same situation. L'Hopital's again. You say you'll do this forever. That's not going to work. So this is not what we would do because last time Jhevon told us You may apply L'Hopital's rule repeatedly. Just simplify between each application to make sure you have to do it again. Right, so because we know how to study and we know that the examples aren't the only thing and all these little things that Jhevon tells you in between the examples is where the real gold is. And we read that and we remember that, we're like, okay, before trying to check about if L'Hopital rules applies again, I should simplify. So I wouldn't even think of doing this. Don't even think of doing this yet. Simplify. So this is going to be equal to, well, keep change flip. You get negative x. You get 1 over x times negative x squared over 1. You get negative x. And what does that approach as x approaches 0 from the right? Well, that's obvious, isn't it? It's 0. Because it's just x, and x is approaching 0. So the answer was 0. This one kind of makes sense, although I do not recommend this, that you think of it this way, because you have the x approaching 0 and the ln x approaching 0, and we know that polynomials move faster than exponentials. So what actually happens here is that the x is getting close to 0 way faster than the ln x is getting close to infinity, and so the 0 wins. So in this case, 0 times infinity was 0. There are times when it's not, so I wouldn't think of it that way, but that idea kind of works out here. Okay, let's do x to the x. Here's an interesting one. Okay, so we see this limit. We look at it. What is it? Boom. As x approaches 0, well, that goes to 0. And as x in the numerator and the power goes to 0, well, that goes to 0. It's 0 over 0, indeterminate. Let's be a little consistent here. I wrote that in red last time. I did. Indeterminate and inconvenient. So yeah, 0 over 0 is an indeterminate form. It's not one of the ones we like, though. We want to rewrite this somehow. And how would we go about doing that? Ideas for this one? So, I mean, one thing I would think here is that a 0 base isn't really the issue. The issue is kind of raising 0 to the 0 power. I mean, if base 0 is raised to any positive number, it's fine. I know exactly what it is. The thing that makes this difficult to evaluate is the power of 0. Because I showed you way back when we were in like lecture 2 or something, that raising 0 to the 0 is kind of equivalent to dividing by 0 in some sense. And so the 0 power is kind of weird. Also, negative powers would be bad because that would, again, lead to division by 0. But 0 is kind of on the borderline of that. It's on the borderline of dividing by 0 versus not. So the power is the issue. So I'd probably say, what do you guys think we would want to do if the power is an issue? Like, what would we think? Where would we?
Well,
what would
when
our?
I tried to do it, I set it equal to y and tried to log both sides, but then I kind of got stuck at this like equation where it's like x to the x. log x. I don't know. It's something like really weird.
Well, that can work, and I'm going to do that method. I prefer a different method, and we can actually do both of them and compare. But along the same lines, remember there was a way that I said we could introduce the log without actually going separately and setting y equals blah, blah, blah? Do you remember that? Do you remember that idea or no? What you said can still work. I don't want to say that, but I mentioned something that I tend to prefer, and sure, I mentioned it. Yeah, this guy right here, right? This rule here in the blue box, it allows us to rewrite things and introduce an ln on something without actually going separately and setting it equal to 0. So we can just setting it equal to y and doing something separately. So we can kind of rewrite things on the spot using this kind of idea. And in fact, we did rewrite something like x to the x in that idea. We know that this is going to be the same as e to the ln of x to the x. We also know that limits pass through continuous functions. So we have that. Since limits pass through continuous functions. Remember, limits can move in and out of parentheses, in and out of radicals. They can move in and out of polynomials. They can move in and out of stuff. So once that thing is continuous, you can actually shift the limit through to the power. Now, I'm not always going to take the effort to write down that step, but you should understand that that's what's going on. And so now, in the power, I can rewrite. The x would come down, because that's what the log allows me to do. And then, notice what limit we have here. Right? We already did this. Right? That was the example we just did above, C. But I'm going to redo it on the spot just so for you to see what it would look like. We'll redo it for science, okay, for completeness. Right, let's pretend that we didn't do this before and this was the original problem. I would rewrite it like this, which, by the way, this whole thing here is just simplifying. And it wouldn't be out of the ordinary to skip to this step. After the first line, especially with a little bit of experience and you understand how things work. You know that, oh, okay, I'm going to have the ln of x to the x. That's just going to be x ln x. And then I put e raised to that. And so jumping to this line right here isn't going to be a problem in general. So we have that, but let's actually continue. In this situation, then I would see I would focus on the limit. I would know that this goes to 0 times infinity, in fact, negative infinity. I'd realize, well, that's not convenient. And so then I'm going to do that whole reciprocal thing. And then I'm going to check again. And I'm going to notice that that goes to negative infinity over infinity. Then I'm going to realize L'Hopital's applies. So I'm going to apply L'Hopital's, indicated by this L apostrophe H that I would put over the equal sign here. And then I would get, this is equal to the limit as x approaches 0 plus of 1 over x over minus 1 over x squared. This is going to be equal to e to the limit as x approaches 0 plus of minus x. And this is e to the 0, which is 1. So 1 is actually the answer here. 0 to the 0, if you restrict yourself to approaching from the right, it is actually 1 is the limit. The reason 0 to the 0 is undefined, just point this out, why I mentioned it was undefined earlier, is because technically there's a hole at this point when x equals 0, and also coming from the left, it does not exist because you would have 0 to a negative power, which would lead to division by 0. So this thing only exists, the limit only exists from one side, and it's not even continuous at that side, but I digress. Yeah, so that's how you'd get that this is 1. Now, alternatively, just to go back to Sarah's method, we could have set y equals the limit as x approaches 0 of x to the x. Then what we could do is we could ln both sides. Right? Is that what you did so far? And what else did you do after this?
I think I just took the derivative, but I don't know. I got lost there at that.
Yeah, but you can't just take the derivative, right?
Yeah.
So remember L'Hopital's rule, you can only do it in 2 very specific situations. So you have to have those situations before you even think about derivatives. Like you wouldn't think about derivatives in the first place. That happened on test 1, by the way. And notice that when I asked for limits, some people were taking derivatives. Like why? Like you weren't in a situation, a limit and a derivative, they're not the same thing. A limit is a very special kind of derivative, sure. A derivative is a special kind of limit, right? So a derivative is not taking the limit as x approaches a of f of x, which is a given function that I would give you. A derivative is the limit as h approaches 0 of f of x plus h minus f of x all over h. Like it's a whole thing. It's a whole process. You don't just randomly take derivatives for limits. In these 2 very specific situations here, we can take derivatives in this very specific way, right? So I don't even really differentiate the thing that I see. I just differentiate the numerator of the thing that I see and the denominator of the thing that I see, right? So here, notice that in the above, we did deal with that limit as x to the x. So we kind of know where this is going because I showed you the alternative. So the idea is how do you get that to work here? Again, it's by this rule. Limits pass through continuous functions. Therefore, what that means is that my limit can move in and out of the ln. I can shift this guy out. Limits pass through continuous functions. Now I can do that thing where boom, 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 can move the x down. And look at that, it's our old friend. We've dealt with this guy like 2 or 3 times today. So I had to rewrite this. At this point, I would look at this limit and realize, hey, that's approaching infinity over infinity. So L'Hopital's applies. So I'll take it to the hospital right now. and the limit would become 1 over x divided by minus 1 over x squared. I can simplify that. Comes minus x. And as I approach 0, I get 0. So is that the answer, 0? It's very important that you realize not the answer.
Oh, I was muted, but I had said no.
Oh, yeah. Okay. It's not the answer. And the reason is, you have to remember, you just logged both sides. You didn't find y, which is the limit you cared about. You found ln of y. What you just found is ln of y. This is what ln of y is. Right? So you then would have to remember, okay, to get y, I would need to raise both sides to the e. So your y equals 1, actually, and that's your limit, right? So another reason why I don't really prefer this method, even though it's not wrong, is that when you do it, not only does it take an extra step for you to go out of your way to set up another equation and deal with it, but it's very easy to get to this point here where you got the 0 and to just forget about the fact that you need to put a base e on it, because you would have forgotten that you're doing the ln of the thing. And this is very common to happen on a test. Right? You're going to be doing this and you just forget because, you run out of time. Jhevon's like 5 minutes left, and you start panicking and you forget. And you just take 0 as the answer, but it's not the answer. You have to realize that you introduced an ln in an equation. You had to undo that ln from the equation to get to the original answer. Whereas over here, that was never a concern, because how I wrote it, the base e was always there. I'm never going to forget it. I was writing it down this whole time, right? The base e was always there. And so that's another benefit, I think, of this guy. But you could have actually written this out a lot shorter, but I was kind of explaining the method. Like I said, either one is preferred. Either one is okay here. Personally, I prefer the first way of doing it. I think it works out nicer. Let's move on to this guy. Limit as x approaches infinity. No. Okay. E. Let's actually figure this guy out. Now, this is actually a guy that we do know. I have mentioned him before, again, a very, very long time ago. Does anyone remember what this guy should give us as the answer? So this is going way back to when I introduced the number e to you guys. And I mentioned a little story about how it was created. It was named for the mathematician Euler, who was studying compound interest and the idea of applying compound interest an infinite number of times per year. And basically I said, well, if you were to take the compound interest formula and everywhere you see the n in the compound interest formula, and if you take that n to the infinity, it's actually equivalent to getting this limit right here. And he found that if you put in $1 at the beginning of a year at 100% interest rate, compounded an infinite number of times per year, you would have E dollars at the end of the year. So this is actually the definition of E. Or you should know. It's one of the first definitions of E that students would come across. if you were to go to Cal 2, which most of you aren't, if any, you would find another better definition of E in terms of power series, but let's not worry about that. So E is the answer here. How would I get to that though? One, I would notice that this guy actually approaches 1 to the infinity. So it is indeterminate. But not convenient. Right? And again, the infinite power is kind of the issue here. Like a base 1 is easy to deal with in virtually any other case, right? Like if I raise 1 to any other number, I know the answer is 1. The problem is the power. So we're going to introduce the ln's, right? So what I would do here is to rewrite this on the spot as e to the ln of 1 plus 1 over x, which is crazy that we're actually using e to derive e, right? Very meta. It's like, was always there, was always the answer. It was meant to be. Like, well, no, I mean, we know the number now and we developed the logarithm on top of it. So we have a nicer way to get to this, much nicer than what Euler had to do. But yeah, we're actually going to use e to figure out e is the answer. It's like 42. So what we can do here is, right, it says e to the x ln of 1 plus 1 over x. Now, at this point, you could move the limit up to the power, but because I know in my head that that's what's happening, that I'm really taking the limit of the power, I'm not really focused on doing that, writing it out. I don't really care. But I do know that this part is going to approach infinity times 0, because 1 over x goes to 0 as x goes to infinity. So ln of 1 plus 1 over x just goes to ln of 1. ln of 1 is 0. Still indeterminate. Still inconvenient. So I would actually do the trick that we saw earlier. Keep the ln, move the x in the bottom, and write as 1 over x. Then I check again. What does that guy behave like? The top approach is ln of 1, which is 0. The bottom approach is 1 over x as x approaches infinity, also approaches 0. This is 0 over 0. L'Hopital's applies. This means I can take it to the hospital and differentiate the top, which is 1 over 1 plus 1 over x, times the derivative of 1 plus 1 over x, which we know is minus 1 over x squared, divided by the derivative of the bottom, which we know is minus 1 over x squared. The minus 1 over x squared would cancel. And as x approaches infinity, this guy is going to approach 0. And that's determinate. I know what that is. This is just e to the 1, which is e by our exponential rules. Yeah. So the limit of this guy, x ln of 1 plus 1 over x, actually approaches 1. Yeah. So that gives us e. Let's go to the other guy. Let's do this guy. E to the x minus x, x goes to infinity. Example E was E, so this is example F. So if you look at this one, let's see where the limit's going. As x goes to infinity, e to the x goes to infinity. As x goes to infinity, x goes to infinity. Ah, that's indeterminate. And inconvenient. So we would try something else. So how do I transform this into something that potentially L'Hopital's rule can work out? Because we have a subtraction here, which is kind of weird. So I know that if I have a power and I want to get rid of the power, I can introduce the ln by that e to the ln of whatever I have kind of idea. So yeah, that's doable. Usually what happens is I get something times the ln, and then I know how to go from multiplication to the division with that reciprocal trick. So ultimately, I know this. So ultimately, I know, we know we can go from, say, powers to products via this guy equals e to the ln of that guy. And from products to divisions via the reciprocal trick. And L'Hopital's being applied to the division. But how do we go from a subtraction to use this idea? How do we go to a division from a subtraction? It's probably a weird idea. But it's actually not that weird. We actually know how to do this. We can go from subtraction to product to division. How would you do this? How do you go from a subtraction to a product? Or more generally, like how do I have a sum of things and I write it as a product of things? Like what is that called? Like what am I doing? Any ideas what that is? It's something you've done all the time. It's not like some weird obscure trick that you tried once that time in high school, in summer school, and you're like, that math teacher was crazy. Like I've never seen that ever again. It's something you do all the time. It's called factoring. That's kind of what it is. Factoring is a way to go from a sum situation to a product situation. I don't know if you guys ever really noticed that, but that's kind of what it amounts to, right? Like when you have like a quadratic equation and you factor one side, like what was the point of that? It's so you could write it as a multiplication, so you could do that zero factor property where, oh, I can set each factor in the product equal to zero, right? Like you went from a sum situation that wasn't convenient to a product situation. So you go from multiple terms spread out, added in a sum, to a single term where everyone was multiplied together. This was factoring, right? That's what it is. And then here, I could use the reciprocal trick. Right? So factoring, you should recognize we can go from sums to products with this technique. Now, here is an important thing. So there were some best practices that you learned with factoring. I do want you to appreciate that those practices were given to you because they were convenient for the purposes that you had. Factoring is a lot more general than you may have thought. So a lot of students would think, well, in order to factor, won't I need like a very special form, like a certain kind of quadratic with certain conditions on it? Or won't I need to have like common terms or something like that? And the truth is no, you don't. You can factor anything at any point. You can factor out anything out of anything except zero. Zero is literally the only exception to that. But otherwise, you can factor out anything out of anything. And that is what factoring is, because factoring, in a very strange way, is kind of like multiplying and dividing by the same thing. Note though, we can factor anything except zero. And you'll see why soon. Out of anything. Including zero. And because what is actually happening when we factor is a convenient. Now, I know it wasn't presented this way because it's actually not very intuitive to present it this way. If anyone presented it factoring this way, everyone would be even more confused about factoring than they already are. And I appreciate that. But now you guys, we're big kids now. We can learn more about the world, learn the truth. Factoring is really a convenient multiplication by one. You're changing the form by multiplying by one in a very convenient way. So for example, if I wanted to factor x squared plus x, we all kind of know, oh yeah, you factor out the common term, there's an x, right? But what actually happens is that you multiply that expression by x over x. And then you left one x outside and you brought in the x in the denominator inside. You do this, and what happens is the inside simplifies to x plus 1. It just so turns out that the perfect thing to multiply and divide by happens to be the lowest power of the terms, of the common terms inside. That's the most convenient thing. I could have multiplied and divided by x squared and moved things in, but then I would get a 1 over x squared in this position. It wouldn't be convenient, right? Multiplying by x over x was convenient, right? Or multiplying by something else like 5 over 5, I could have done that. It would not be convenient though. It wouldn't give me the essence of what I want. I would just have a 5 on the outside, x squared over 5 plus x over 5. It wouldn't make a difference, right? The common term was the perfect thing to multiply and divide by in order to make some sort of useful rewriting of the thing. So the common term, so this is the common term. The perfect thing to multiply and divide by. But it wasn't necessary. So for example, if I had like e to the x plus x, I could still factor out an x if I want, because factoring out an x means multiplying and dividing by x and moving an x inside. Right? So I can still get to a factorization here. So of course, normally you would skip over this traditionally. We skip here. And so, yeah, I have e to the x plus x. X is not a common term here, but it doesn't matter. I can still factor it out. You know, so I'm assuming my x is not 0. I can factor it out. You can always factor out anything other than 0. And the reason is because factoring out is like you multiplying and dividing by the same thing. And we know we can't divide by 0. So 0 is the exception to this. You can't factor 0 out of anything because then you have zeros in all the denominators. But you can factor anything else out of anything else. So that is what we're going to do. Okay, so that was a very long detour. Just to kind of introduce the trick that I was going to use here, the trick is to factor. Once I can factor, I get it as a product. Once I have it as a product, I can change it to a division. Once I have a division, there's hope for L'Hopital's rule if it's a 0 over 0, infinity over infinity indeterminate form. So it was infinity, which is not 0, which is good. So this is infinity minus infinity. And then what I could do is I could factor. Factor out an x. I would end up with e to the x over x minus 1. So this is why factoring, when you pull something out, you actually subtract the power of that thing to every term on the inside. Or you can even think of it as multiplying every term on the inside as that thing to the negative power that you pulled out. And that's why factoring simplified that way, because it was like a convenient division by 1, actually. You're actually dividing everyone inside by the thing you factored out. So now it's a factor. Now it's a product. I have x times something. Now the x is going to infinity. And what about the thing inside? Well, we saw this goes to infinity last time. Yeah, you can apply L'Hopital's rule. You can also just know, well, it's an exponential divided by a polynomial. It's top heavy as you're going off to infinity. The e to the x is going to overwhelm the x. So we're going to get infinity anyway. So this becomes infinity right here. Right? So now you have infinity times infinity. What is that? Is that indeterminate? Do we need to do something else? What is infinity times infinity?
Infinity squared.
Sure, but what is that? Like, how would you describe that based on what we're doing? Huh?
Isn't just infinity?
It's just infinity. It's not indeterminate, is the point. I do want to emphasize that this is not indeterminate. You don't have to do anything fancy here. You can evaluate that at face value. You have a huge number times a huge number. I know for sure the result is a huge number. There's no competing ideas here. It's infinity.
Wait, so if you have 0 times infinity, wouldn't it just be 0 though?
No, that's the point. Like, that's what I'm saying, because 0 times anything should be 0, but infinity times anything should be infinity. Like, there are two competing ideas there. You're not sure if the 0 is going to win or the infinity is going to win. Because if you have something like, well, we saw earlier, like when we had x times ln x, as x was approaching 0, this went to 0 times infinity, and we found that this was 0, was the answer. It does not mean you always get 0, because there are cases where you cannot get 0. So for example, I want a nice example, but off the top of my head. Something like x cubed times 1 over x squared. Or the other way around, x squared times right? This one also approaches 0 times infinity, right? Is the answer 0 in this case? Well, no, because if you simplify this, it becomes 1 over x. And we know that that actually equals infinity. So here, 0 times infinity is infinity. Here, 0 times infinity is 0. Like you don't actually know for sure who's going to win. It depends on the functions that you're looking at. I could also get it equal to anything. Like I could have the limit as x approaches 0 of 5x squared times 1 over x squared. Technically, this approaches 0 times infinity, but obviously this just simplifies to the limit of 5. So 5 is actually the answer. So over here, 0 times infinity is equal to 5. Like it can be anything, really. It's like it's indeterminate. You don't know, right? You can't evaluate it at face value. It very much depends on the specific example you're looking at, right? So all the indeterminate forms I give you, do not try to think, oh, well, that's probably a 0. Like, don't do it. Like, if you don't know what it's going to end up being, right? So, yeah. In this case, infinity minus infinity was infinity. It didn't have to be. It could have been anything else. It could have been 0, could have been 5, could have been 17. You don't know until you actually rewrite it some convenient way. In fact, I think I have a nicer example of infinity minus infinity later on. Like this one is such an example. X approaches 1 from the right of 1 over ln x minus 1 over x minus 1. Okay, we're approaching 1 from the right. What's going to happen? Well, we know the graph of the logarithm. At 1, log hits 0. On the right side, it's positive. So approaching 1 from the right is like approaching 0 from the right side. So this is 0, 1 over 0 plus, minus. If I have x is approaching 1 from the right, that means x is a little bigger than 1. If I subtract 1, it's slightly positive. So this again goes to 0 from the plus side. And so this actually gives us infinity minus infinity, right? What is that in this case, right? Is it 0? Is it infinity? Is it negative infinity? Students might see, well, I see what Jhevon's trying to do. He's trying to see if I remember that rule about how functions behave. So because I know that the polynomial is going to go to 0 faster than the logarithm, what that means is the 1 over 0 plus on the right side is going to be like get to infinity much faster than the 1 over 0 plus on the left side. And so it's going to kind of be like something very small, minus infinity. So the answer should be minus infinity. And then you're going to think, you're trying to evaluate it at face value with some sort of argument, some story, some meaning that you want to inscribe to it. But you would be wrong in that case. You cannot evaluate this at face value. You have to go through the motions of doing the calculations, right? Let's see what infinity minus infinity is this time. Last time it was infinity, because you could argue, oh, one is much bigger than the other. But can you make that argument in general? The answer is no. And you shouldn't have made that argument here either. Factoring and figuring it out is what you should have done. So, all right, we're in L'Hopital's rule. The nice thing would be to have a division. I have 2 divisions. So the nice thing to do would be to combine them. Combine into one fraction. So this would be x minus 1 minus ln x over x minus 1 times ln x to combine in a simple fraction, in a single fraction. What happens now? As x approaches 1, x minus 1 would approach 0, ln of x will approach 0, so that gives us 0 in the top. As x approaches 1, x minus 1 is 0, ln of 1 is 0, so I have 0 times 0 in the bottom, that's 0 over 0. L'Hopital's applies. So let's actually do that. Differentiate the top. I would get 1 minus 1 over x. Differentiate the bottom. I would need the product rule. It's going to be ln x plus x minus 1 over x. Right? I applied L'Hopital's here. Took it to the hospital. Where I applied product rule in the denominator. Now, do we do the check again? Simplify first. We learned our lesson. Hopefully you learned the lesson. I feel like I spend more time writing out all these side comments than I do doing actual examples, you know? So it kind of breaks my heart when I put a problem on a test, and it's very easy to do it had you read the little side comments that I was making. But students either don't know how to do it or they go off and do something extremely complicated. Breaks my heart. It hurts me right here to take those points away. It does. So we would simplify first. You could do that by multiplying by x over x. Because I mentioned in another side comment a very long time ago that that is the quickest way to simplify a complex fraction. Some students will go through the whole thing of, oh, let's combine the fractions in the top and then combine the fractions in the bottom and then keep, change, flip. You're wasting time. Multiply and divide by the LCD is the quickest way to simplify something like this. So that gives you x minus 1 in the top. It gives you x ln x plus x minus 1 in the bottom. Now we do the check. Is it determinate at this point? Turns out you would get 0 over 0 again. Ah! Hey, L'Hopital's rule applies. So let's do it again. Let's take it back to the hospital. We didn't fix the issue last time. Derivative of the top is 1. Derivative of the bottom by the product rule is ln x plus 1 plus 1. Product rule. I did that over here too. All right. Now what do we have? Notice that now it's definitely not an indeterminate form because I have 1 in the numerator, right? Then in the denominator, as x approaches 1, ln of x is going to approach 0. So this is going to approach 1 over 0 plus 1 plus 1. Infinity minus infinity is a half here, which is kind of silly to think about, but it is the answer. Okay, so those were just some examples on L'Hopital's rule. Just a nice little trick to deal with certain kinds of limits, so we can deal with even more difficult limits now. Yeah. So now hopefully some of you get those memes that I put on a quiz a long time ago about, you know, how, you know, students like any limit they see, they try to take derivatives and hit it with L'Hopital's, and it's like, no, you're not allowed to do that. Yeah, so, all right. Let's actually introduce another topic. The next thing I want to do, and this, I believe this is the last section in chapter 3 that we want to cover. section 3.2, taking it back, linear approximation. And I feel like the scale is off here. And marginal analysis, which is sort of an economic application of derivatives. They're both sort of applying derivatives in the same sort of way. Let's start with linear approximation. And what this is, it's a super important application of derivatives. Yes, derivatives are nice for finding maxes and mins and when functions are increasing and decreasing, but a lot of applications uses linear approximation because sometimes we want to deal with very difficult functions and we want to use a tangent line to approximate them, like we did with the folium of Descartes. And so the idea is using a tangent line to a function at a point to approximate outputs of that function. At nearby points. Right? So the idea is you're using a line to approximate something, linear approximation, right? So that's essentially what we're doing. So how does it actually work? What does it mean, Basil? Let's actually see. So, and why you would even need to do this is because the function itself can be quite complicated in the beginning. In fact, I'm going to mention an example where the function was like impossible to figure out. So here's our function. Let's say this is our f of x. And let's suppose at this point right here is input A, and the output is, of course, f of A, right? And let's assume f of A is known as well as f prime of A. So we can construct a tangent line. I think that's going to get into the way of what I want. Actually move this down a little bit. I'm going to annotate this diagram a little bit more. Okay, so what we can do is we can get a tangent line to this thing. So that's our tangent line. Okay. Now here's the thing. Suppose there is some nearby point that I care about. So this here is the point where we have all the information. This is some nearby point. Now, of course, what I would like to do you have to make the sound, is figure out what is f of x at that point, this nearby point. I'll write that somewhere else. Okay. But maybe for some reason that's difficult or next to impossible for me to actually figure that out. What I can do instead is just go up a little bit further, hit the tangent line, whose equation is going to be super easy to compute and know what its output is, and output some other value. Call it y sub t. So tangent line y sub t of x. Okay. And I can use the y sub t as an approximate value of the f of x. The idea is if the x is close enough to the a, the y sub t and the f of x would actually be close together themselves. So the idea here is, can I use another color? If you were to think about the y value at the beginning and the y value at the end, what I care about, this is what's called the change in y, right? That's your delta y, right? One y value minus the other. However, if I look at the change in the original value to the change in what the tangent line would have done, this is what's called dy, right? That's where the derivative helps us to find, right? Like that's the dy in dy dx, right? That's what it is. It's actually a distance, right? This distance here would be what we call delta x, which is actually equal to dx. So dy over dx gives us the derivative. That's the rate of change. That's the change in the change approximated by the tangent line. Delta y over delta x is the actual rate of change. Yeah. So now the idea is if x is close to a, dy is approximately the same as delta y, and so we can use the tangent line y sub t of x. Oh, that's a very weird x. To approximate f of x. But what is y sub t? We know yt minus y1 equals mx minus x1, where this guy is the derivative evaluated at the point. That's how we get a tangent line. This guy is the input at the point. This guy is the output at the point. So it turns out that our y sub t minus f of a is equal to f prime of a times x minus a. In other words, the equation of the tangent line is f of a plus f prime of a times x minus a. And the assumption is when x is close to a, our f of x will actually be very close to the output of our yt of x. And so this is actually the f of a plus f prime of a times x minus a. So that tells you that your f of x is approximately f of a plus f prime of a times x minus a. This is, I don't know why it does that. This is called the linear approximation formula. And so you see we can use the tangent line to approximate the output of the function. Let's do a quick typical example, and I would give you guys another one. So chances are an example in your test, and an example in the bonus on the test would look like this, by the way. Use linear approximation to estimate the square root of 3.99.
Thank you.
Okay. So what you would do is, one, set up a function whose output can approximate what you want. Now here, you want to approximate a square root. The function might as well be the square root of x. The second thing you're going to do is you're going to find the derivative. So we know the derivative of f of x is 1 over 2 rad x. The third thing is now you're going to choose your x and your a, where the x is the ugly value you want to approximate. F of x for, right? All numbers are beautiful, you know what I mean. A is a nice value close to x for which you know f of a and f prime of a for, or you can find them. Relatively easy. So here, your x is 3.99, and a, you would choose 4. It's the closest value to 3.99 that you know all these answers for. And so moving on to the next step, you're going to evaluate f of a and f prime of a. So here we know our f of x is radical x. This means our f of a is going to be f of 4, which is rad 4, which is 2. We know that. Our f prime of x is 1 over 2 rad x. This means our f prime of a is f prime of 4, which is 1 over 2 rad 4, which is a quarter. So we could find those easily. Final step is to plug into the linear approximation formula. So here, I know that my f of x is approximately equal to f of a plus f prime of a times x minus a. And so my square root of 3.99, well, that's just f evaluated at 3.99, but that's approximately equal to f evaluated at 4 plus f prime evaluated at 4 times 3.99 minus 4, because this is the x and this is the a, the x, the a in that formula above. This is 2, this is a quarter, this is minus 0.01. In other words, this is 2 minus 1 over 400. 2 is 800 over 400. So this is 399 over 400. And that would be the approximation. So now you know how to do the bonus problem on the test. This is the idea that you should have done. I'll let you guys go, but first, I just want you guys to see, for fun, our 399 over 400 what is that actually equal to? 399 divided by 400. No, that's not 399. What am I talking about? 799. It was 800. 2 is 800 over 400. Not 400 over 400. I was thinking of 1. Let's see. 799 divided by 400.
It's like 1.99.
9975. Now, what is the actual value? Actual from calculator of the square root of 3.99. So I go to my calculator, square root 3.99.
The same.
It's 1.997. Ooh. 4. Ah, we messed up. 843. It goes on forever, right? However, look at that with rounding. Gasp. We're accurate up to 4 decimal places. And I did that by hand, right? I calculated the square root of 3.99 correct to 4 decimal places in my head. Like, who does that? Like, am I a math savant? No, I use the tangent line, right? Look, ma, no hands, right? So now, that's just to illustrate the power of this idea. And I mean, being like 0.1 units away is a huge distance in math terms. Like, what? You might as well be forever away. That's not close. Like, no mathematician would think of 0.01 as close. So yeah, really interesting. Try this again for something, and try this for the cube root of 8.01. Tell me what answer you get, how many decimal places accuracy you can be. But for now, we will stop there. And next time, I'll also talk about a nice application of linear approximation. But this is the problem type that you need to know. Like, I'm always going to ask you a problem like this, like, spoiler alert. Here's some weird number, use linear approximation to estimate it. Right? That's all we can really do in Applied Calc 1. I'm not going to make it any more difficult than that. Okay, so that being said, that's it. Thank you for your time and attention. There are no classes tomorrow. No classes on Friday. It's Good Friday. Doesn't affect us, but if you have anything else on Friday, you should know that there are no classes. I'll see you guys on Monday. Have a great weekend. Make sure to look over your test on Gradescope and submit regrade requests if you haven't already. I know a lot of students did not do that, even though they should have. So yeah, do that, and I will see you guys in the next one. Ciao.